Most individuals dream of learning to drive and owning a car. A lot is involved in owning a car, starting with the financing of the vehicle. Once a car is purchased, its value begins to decrease. The owner must also be concerned with the resale value of the vehicle. Now, let's start with saving for the purchase of the car. Sometimes individuals will set aside money in savings accounts that pay interest. Hello. In this video project phase, we're going to deal with exponential growth and decay. Exponents and exponential functions will be shown using those two concepts. We'll use the idea of automobile purchasing to represent exponential growth and the automobile depreciation to represent exponential decay. Now, let's get to it. Suppose you put $1,500 in a savings account that pays interest at the rate of 8% per year. The $1,500 is the initial amount that's deposited, while the 8% is the interest and the year is the interest period. Your interest period is the length of time over which your interest is calculated. Now let's take a look at a table and see how the money will grow over the years. $1,500 over the years, being our initial amount, will grow in 1 year to $1,620 because the initial amount has added to it our initial amount times the amount of interest accrued. The second year will give us a total of $1,749.60 being accrued, with the interest being applied to the $1,500 over a 2-year period. The third year will have $1,889.57 after having applied 8% interest to the $1,500 over a 3-year period. The fourth year will have $2,040.73, and so on. This is how the money grows with interest being applied to it. To be able to get a formula instead of having to do the math manipulation we just saw every time you get ready to figure out how much money you will have at the end of a certain number of years, the pattern yields the formula of your previous balance being added to the interest earned, equaling your new balance. Now, notice that the interest is added to the balance. This is called compound interest. Compound interest is the interest on both the principal, the initial money invested, and the interest an account has already earned. If you'll notice in the table we have now, we have at 0 years our initial investment of $1,500. And then we've got the property of 1 being used in the first year for 1 times $1,500 plus our interest for the first year, 0.08%, 0.08 equaling 8% times 1,500. To get our total amount, we then multiply 1,500 times 1 plus 0.08, since this is our first year. Here, the distributive property is implied. To finish this, we take 1.08 and multiply that simply times 1,500, since we are accumulating money, giving us a total amount of $1,620. For our second year and concurrent years, we take again our interest rate of 1.08 times our first year balance, and that would give us 1.08 times 1.08 times 1,500, since this is our second year, giving us a balance in our second year of $1,749. Look what we do in our third year. We've got 1.08 times 1.08 times 1.08 times 1,500, giving us 1889.57. You see the pattern? For each year, the factor of 1.08 matches it, times 1,500 in our fourth year, giving us $2,040.73. Now, since for our purposes we're using 1.08 as a factor, the resulting function we come up with when we look at the pattern in the tables we just observed is y is equal to 1,500 times 1.08 to the x power, x representing the number of years our interest is to be compounded for. This is called an exponential function. An exponential function is represented by y is equal to a times b to the x, where a and b are constants for all numbers a and for b greater than 0 and b not equal to 1. Dealing with our exponential function. This function represents exponential growth, a times b to the x. Our money is growing, so we've got 1,500 times 1.08 to the x power, again, with our x representing the number of years, b representing the growth factor, a representing our initial deposit, and y is the balance in dollars that we'll have after x years as our money grows. Now, since we have seen how an exponential growth formula can be developed, let's take a look at the picture that an exponential growth formula or equation will generate in the graphing calculator. If we take the initial deposit, let's go into Y1. Take the initial deposit, enter it with our interest at X number of years, that being our general formula to be able to find the amount of money we'll have after any number of years on the $1,500 deposit. Take it and graph it. If you use a zoom, since it's going to be an exponential growth, to be able to get a good fit in your graphing calculator, if you'll use zoom fit, which is at 0 in the zoom menu, hit enter, that will cause the graphing calculator to automatically adjust a window so that you can see a good picture of the function being generated in your graphing calculator. Now we have a picture of what our interest formula looks like. To be able to see the actual numbers that cause these points to be generated by the graphing calculator, we can look at the table. Before we do that, though, let's go back and use our trace feature to determine how much money we have at X number of years. If you'll hit your trace button, you'll see that at 0 years, which is our X value here, we have $1,500 represented by our Y value. You remember back at the beginning, we talked about our Y value being the balance of dollars after X years. Now, use your right button and trace to 1 and find out how much money you'll have. You remember in the table, after 1 year, we had $1,620. After 2 years, let's see if we can get a match here for 2 years. After 2 years in our table, we came up with $1,749.60. After 3 years, the money generated by having invested $1,500 at 8% interest is $1,889.57. Of course, the bank will only say it's 56 cents since the bank does not round up. After 4 years, we've got $2,040.73. This is called an exponential growth picture because the y values increase repeatedly by the multiplication of a number greater than 1. We're multiplying repeatedly, $1,500 repeatedly by 0.08. We're multiplying $1,500 repeatedly by 1.08. The number of times it's being multiplied by 1.08 is represented by 1.08 being raised to the x power. Now let's take a look at the numbers. Go second table, and this gives you the number of numbers. This gives you the numbers, the points that actually made up the graph that we just saw. The ordered pairs, the x values again in our ordered pair represent the number of years. The y values represent our resulting amounts in our account. After 10 years, we see we'd have $3,238.40. 15 years, we'd have $4,758.30, and so on. The numbers in our graph represent exponential growth simply because the numbers that are resulting are graduating or growing according to the number of years that 1.08 is being raised to. Again, take a look at the picture, and we have growth represented in our picture that correlates with the numbers in the graph. Now, since we have taken a look at exponential growth, we're going to turn the tables and look at the opposite, exponential decay. We'll look at exponential decay from a car salesman's point of view. From the time a car salesman purchases a car and has it on his used car lot, the value of that car begins to depreciate. Normally, cars depreciate on the average of about 30% per year. So, let's take a look and discuss the purchasing of a car from a car salesman's point of view. Since we're assuming that automobile value depreciates at the rate of 30% a year, in the table we see the first year, if a salesman purchases a car at $12,000, the $12,000 gets multiplied times 0.7, causing the car value to become only worth $8,400 after the first year. The second year, the previous balance is multiplied by the amount of depreciation, or the worth of the car. The actual worth of the car is represented here by the 70%, since 30% is taken off per year, giving us a resulting value of $5,880. The third year, we've got the previous balance of $5,880 being multiplied by the worth of the car after its depreciation, 70%, resulting in $4,116. The fourth year, the same thing, the previous balance, $4,116, being multiplied by the after depreciation worth of the car, causing that car to further depreciate to $2,881.20. Now, just as we did before with exponential growth, we can develop a formula. There's a pattern in this information. If we can take a look at what's happening, you'll see that the same type of pattern occurs here as did before in our exponential growth. Here we have, in our exponential decay, the initial amount being multiplied times the amount of the worth of the car after depreciation raised to the power for the number of years we're calculating it. Again, the amount of the car being multiplied times the amount that the car is depreciating, the worth of the car, raised to the number of years we're calculating it for. Again, the pattern is to take the initial amount multiplied times the worth of the car, raised to the number of years that it's depreciated. The worth of the car times the worth of the car raised to the number of years of depreciation, giving us the worth of the car at that time. Generating the formula, y times is equal to a times b to the x, the same general formula we use for our exponential growth, but for depreciation, instead of having 1 plus the amount of interest, we simply have the amount of interest involved, giving us, for our depreciation formula for our car, 12,000 times 0.07 after 30% interest, 30% depreciation raised to the x power. Again, with x being the number of years of depreciation, b representing the decay factor, a representing the cost of the car, and y being the value of the car after the number of years of depreciation. Everyone should be interested in knowing this formula, because once you buy a car, this is what happens to it. It not only happens to the car lot salesman's cars, it happens to yours also. From the point you drive that car off of the lot, it begins to depreciate. And this is the formula that you can use to determine the worth of your car at any point in time. Now, let's take a look at exponential decay. Exponential decay is y values decreasing because of repeated multiplication by a number between 0 and 1. As exponential growth was, y values increasing because of repeated multiplication by a number greater than 1. Now, since we have discussed both exponential growth and decay, to get a practical look at what they look like when you graph them, let's take a look at the graphing calculators with the graphs for both exponential growth and decay side by side. In the graphing calculator to your left, you'll see you have the function that we discussed at the beginning of this project for exponential growth, when we were wanting to save money, when we wanted our money to grow. You've got 1,500 times 1.08, since our money is growing at the rate of 8% per year, raised to the x power. Notice, for exponential growth, the factor is greater than 1. For exponential decay, the factor is between 0 and 1. For our automobile depreciation, we've got 12,000 as the initial cost of the car, times the worth of the car after 30% depreciation, leaving us with a 70% worth raised to the x power. X being the number of years it depreciates, or x being in our growth, being the number of years the money grows. Now let's take a look at the actual pictures the calculator will generate for us from these formulas and compare the pictures for exponential growth and exponential decay. Marked differences. The exponential growth formula causes a curve that ascends parabolically to the right, and exponential decay causes a curve that decreases toward the x-axis to the right. Those are your physical differences. That's how you can tell what kind of formula has been used to generate either kind of curve. Again, you have your exponential growth curve on your left and your exponential decay curve on your right. Now that we have actively participated in the ups and downs of functions, let's take a look at actually what we did. We talked about exponential functions, we defined it. We talked about exponential growth and looked at a picture of it. We talked about the growth factor that's involved in exponential growth. We also defined compound interest and the interest period. We talked about a decay factor. We talked about the difference between our growth factor and our decay factor. We also talked about and experimented with exponential decay. Since we have looked at and examined exponential growth and decay thoroughly, now we know how to manipulate the functions called exponential functions. Get ready to do the exercises that your teacher will supply you with to further reinforce your knowledge and your use of this information, so that when you get ready to get out in the world and use this information, it'll be at your fingertips call. Have fun. Thank you.